So why do we talk about the normal distribution?
Well, knowledge of the distribution of observations tells us a lot. Which ones are most likely and how widely they're spread. And many of the traits of interest to us follow a normal distribution, so actually it underpins our thinking about statistics.
So here we have a graph of the normal distribution. On the x-axis we have some measurement which is made on an interval or continuously variable scale, and on the y-axis we have frequency, which could be recorded as either the number of observations or the proportion of the total number of observations, and measured on a scale of 0 to 1. The normal distribution curve is described by the population mean, for which we use the Greek letter mu, and also by a measure of its variability, described as the population standard deviation, for which we use the Greek letter sigma.
The normal distribution is what we call a probability distribution. Observations near the mean occur with a high frequency or high probability, while those observations which are distant from the mean occur with a lower frequency or lower probability.
The normal distribution is a family of distributions, all of which are described by their means and by their standard deviations. The greater the spread of values that we see, the larger the standard deviation. Here we have a distribution of a population of heights. The mean value mu has a value of 1.75 meters, and the standard deviation has a value of 0.1 meters. If we take a range from the mean plus or minus a single standard deviation,
what we find is the lower limit of that will be 1.74 meters and the upper limit will be 1.76 meters. And what we find is that 68.2% of all observations fall within that range.
If, however, we take a range from the mean plus or minus 2 standard deviations,
the range now extends from 1.73 meters at the lower end to 1.77 meters at the higher end. And what we find now is that those limits contain 95.5% of all the observations.
And then for our final example, if we take the mean plus or minus 3 standard deviations,
that extends from 1.72 meters to 1.78 meters, and we find that 99.7% of all observations fall within that range.
So this table summarizes the information that we've just looked at, and the important point to notice is that it is true for any normal distribution, whatever the value of mu or sigma. So if you know the mean and the standard deviation of a population, you can say what proportion of values will lie within the range from the mean plus or minus 1, 2 or 3 standard deviations. Now, if we look at this from a slightly different angle and take a range from the mean plus or minus 1.96 standard deviations,
we find that range now extends from 1.554 meters at the lower end to 1.946 meters at the upper end, and we find that those limits actually contain 95% of all observations. And we're left with 2.5% of the observations at one end of the distribution and 2.5% of all observations at the other end of the distribution.
Similarly, if we take a range from the mean plus or minus 2.58 standard deviations,
we find that this range contains 99% of the observations. with only 0.5% of the observations at the lower end and 0.5% of observations at the higher end.
And finally, if we take a range from the mean plus or minus 3.27 standard deviations,
we find that those limits contain 99.9% of all observations, with only 0.05% of observations in either end of the distribution.
So summarizing, we can see the ranges which are required to encompass 95%, 99 or 99.9% of the total observations.
And this is true for any normal distribution, whatever the value of the mean and whatever value of the standard deviation.
Why is this such an important result?
Well, one, because it's true for any normally distributed population, and that covers a lot of our interests. And secondly, it forms the basis of many of the statistical tests that we use.
Explain.
Ideas of probability and rarity underpin a lot of what we do in statistics. If we record an observation that's within 1.96 standard deviations of the mean, it's a fairly common occurrence. It happens 95% of the time. But if it's outside 1.96 standard deviations of the mean, it's a relatively rare occurrence and happens once in every 20, about 5%. Outside 2.58 standard deviations of the mean, it's a very rare occurrence, 1 in 100, 1%. And if it's outside 3.27 standard deviations of the mean, it's an extremely rare occurrence, 1 in 1,000, or 0.1%.
So, we could take the value of any observation and express it in terms of the number of standard deviations it is away from the mean, and see how likely or unlikely it is for the population.
Yep, we call this quantity Z, and if we were to put it into mathematical terms, we'd say Z equals the individual value minus the mean divided by the standard deviation, where the standard deviation and the mean are known population values. Suppose I told you that a breed of dog had a mean height of 40 centimetres with a standard deviation of 1.5 centimetres, and that I'd measured a dog that was 45 centimetres tall. Do you think that this dog belongs to the breed I describe?
Well, Z will equal the mean minus the observation divided by the standard deviation. So 40 minus 45 divided by 1.5 equals minus 3.33, which is bigger, if we ignore the sign, than the 3.27 cutoff for 99.9% of the population. The chances that it belongs to the breed are therefore less than 1 in 1,000. At 1 in 1,000, I'd put my money on it belonging to a different breed, but I guess I might be wrong.
Exactly. Statistical methods don't prove your point. They allow you to balance out the odds of different outcomes and set a level of confidence in your conclusions. By convention, we set our levels of confidence at the 5%, 1% and 0.1% limits. The lower the value, the more confident that we are, but we might possibly be wrong.
I understand this Z business relative to individual observations, but that seems a pretty limited application to me.
Well, it is, but suppose I had a sample of 10 dogs with a mean height of 45 centimetres. Are they from the target breed we were talking about?
I'd say it was extremely unlikely to take a random sample from this breed and get such a high mean value.
Yeah, I agree. Such an extreme value for the mean of a sample of 10 dogs seems highly unlikely when individual values of that level are so rare. We'll use that insight when we explore methods to compare the difference between the means of 2 or more samples. Right.
So to summarize, many continuously variable traits follow the normal distribution.
The distribution is described by the mean, mu, and the standard deviation, sigma.
And the position of an observation is described by the formula z equals x, the value of the individual observation, minus mu, the value of the mean, divided by sigma, the value of the standard deviation.
With 95, 99 and 99% of observations within the range mu plus or minus 1.96, 2.58 or 3.27 standard deviations of the mean respectively.